Sorry. So the next talk is about Iris-WasmFX, and the presenter is Maxime Legoupil.
Hi everyone, good morning. I'm Max, and today I'll be talking about Iris-WasmFX. It's a work that's at the confluence of three main topics: the WebAssembly programming language, the Iris separation logic, and the use of effect handlers as a programming technique. So let me walk you to how we get there in the middle. The starting point for us today is WebAssembly. WebAssembly is a very unique programming language in that it's both something that's very widely used and cared about. It's not a toy language, it's not a simplified version of something else, but it still has a fully defined formal specification, which makes it relatively easier to do formal reasoning on the language. And so we looked at proving some formal properties about WebAssembly. The thing that we were originally interested about was local state encapsulation, a property that is very cared about in WebAssembly. And what this means is that the code in WebAssembly, organized in modules, should not have one module A arbitrarily meddle with a module B's inner state. Module B's global variables, functions, memory should not be arbitrarily accessed by module A unless module B has specifically, explicitly tagged an object as being exported. And now the way we've gone about to do this kind of formal reasoning work is by using separation logic, and more specifically the Iris separation logic. Iris, if you've never heard of it, is a framework for logic that has an implementation in the Rocq proof assistant. And the way it then works is if you're able to describe the operational semantics for your language in Rocq, Iris then gives you a lot of tools and a lot of rules to then reason about programs written in your language. I'll show an example in just a second. And so we wondered if we could use this separation logic to reason about an actual real-world language like WebAssembly, and the answer was yes. We defined Iris-Wasm a couple of years ago, which is a program logic that helps you reason about programs written in WebAssembly. This is going to look something like what I have over here. My precondition P implies, with this little magic wand, which is our separation logic implication, a weakest precondition on my program E. And what this means is that my program E is going to run without ever getting stuck. And if it ever terminates on a value V, then my postcondition Q holds of that value V. So for example, I've showed here what this could look like for a very simple program that just retrieves the value of a global variable. I have to assume that I have this resource corresponding to my global variable G, imagining that G points to V0. Then I'm able to safely run this program that's just one instruction, get global variable G, and at the end, I will still own that resource corresponding to global variable G, and using this star, which is my separating conjunction, I know that the value that I get back, that I terminate on, is going to be that value V0 that I have in my value G. And so using this logic, we have formally established this local state encapsulation property, which now means that this property that we probably already knew was holding is now formally stated, formally verified. But more importantly, we now have a starting point to reason about new variants of WebAssembly. WebAssembly is a very, very vibrant research ecosystem. New versions are proposed all of the time. And a lot of the time, these new versions can be thought of as WebAssembly where you're adding a new feature. And because Iris is also a very vibrant research ecosystem, that feature has oftentimes already been reasoned about in Iris and is well understood in the world of separation logic. So we thought maybe in those cases you could massage all of these existing works together to get a program logic for your new version of WebAssembly. And I'd like to stress here that even though I'm using this kind of visual with a Venn diagram, this is a lot more complicated than taking just the intersection of existing works. There is a lot of work involved in doing formal reasoning about industrial-sized languages. But we argue that this is something that gives us a lot in return, and that we should still see this effort through, because everybody kind of wins something when you do this work. The WebAssembly community gets to have their new versions validated, completed. We can find bugs in some instances, and it's really a useful feature to encouraging adoption of these new versions to have formally verified properties. The Iris community gets to see the logic exercise at an industrial scale, and that sometimes highlights places where the logic should be completed or new needs The new feature community also gets to see their features studied at a real-life scale with new formal tools being developed. This kind of roadmap to reason about a new version of WebAssembly has already been successfully applied to memory-safe WebAssembly. There is a version for rich Wasm that is on the way, and today I'll be speaking of Iris-WasmFX, a version of WebAssembly with effect handlers. So for the rest of this talk, I'll introduce WasmFX and our logic with regards to reasoning about programs written in WasmFX. If you've never heard about effect handlers, they're a programming construct that is increasingly popular because it allows to, in specific circumstances, it will allow for a lot more efficient programming. You can think of it as kind of an exception where you would throw back control flow to a handler somewhere higher in the execution flow, but you can then later resume and come back to that point where you have thrown that exception. These are known under a number of different names. Call CC and throw is probably the most common of those. So if you've ever seen that, that is effect handling. Async, await is another way of doing this. In WebAssembly, these are called instead resume and suspend. So the version of WebAssembly with effect handlers that was introduced a couple of years ago introduces a couple of new instructions. Cont new creates a new instruction. Resume runs a continuation that was created with cont new, and suspend triggers that effect to throw that control flow back up. I'll show an example just in the next slide. Just before I show this example, I'd like to mention very quickly this last instruction on my slide, switch. I'm mentioning it because it is something that a lot of industrial users of WasmFX care a lot about. It can be almost full as some syntactic sugar, suspending and immediately resuming something else. I want to mention that we have implemented that instruction in our programming language, but it makes a lot, in our program logic, but it makes the logic a lot more complicated, so I'm not going to be mentioning it anymore in this presentation, just for simplicity. So we'll just focus on the first three instructions, new, continuation, resume, and suspend. And to understand how these work, let's just have a look at a simple example in WasmFX. I've got two functions here. On the left, I've got my auxiliary function. If you've never seen WebAssembly code, it's written like this as a list of instructions, and you can think of it as a stack-based language. I'm putting one onto the stack, and if you ignore the suspend for one, for now, I'm then putting a second constant 2 onto the stack and then adding them. So this function is basically just doing 1, 2, and then adding those 2 into 3. But as you can see, I've got a suspension here, suspended to the tag T. That's just how I differentiate different kinds of effects that can be introduced. In all of my examples, I'm only using one effect for simplicity, but that's kind of like when you define your new exceptions, you could have many different names here. And to understand exactly what this suspension does, we need to see the code that is actually going to invoke the auxiliary function. That's my main function here on the right. Again, if you've never seen WebAssembly code before, this might look a bit convoluted, but it's organized in blocks like this. I'm just going to enter these blocks. I'm entering block 1, block 2. I'm creating a new continuation from this auxiliary function aux and resuming it immediately. So now I'm running this code. But then when I see this suspension, a bit like when I'm throwing an exception, I will come back to this resume instruction and see if my effect is being handled. And it is here. I have an instruction here that says on T, exit block 2. If I hadn't seen a suspend, then I would have just executed the next instruction here, which is unreachable. So I better see a suspension. But I do see a suspension. It's right here, and it's handled here on T, exit block 2. So I'm going to exit this light blue block, and I find myself in this instruction. At that point, the continuation that I was running and that I have suspended is on the stack. So if I have this resume here, what I'm resuming now is what I was just running earlier. So now I'm going back into my function and resuming the execution. As you can see, I'm saying on T exit block 1, meaning if I see another suspension, I will now be exiting block 1, this yellow block. And then I will see this unreachable instruction. So I better not see another suspension, but all is well because I'm just seeing 2, add, and then this function terminates, and I execute what happens after the resume, which is a return. So this is a very convoluted way of just computing 1 plus 2, which is 3. If I want a slightly more complicated example, I can imagine that my tag is now given a slightly more complicated type, int to int. And what this will mean is that I will carry a payload when I perform my effect. So again, my main function is going to create a new continuation corresponding to my auxiliary function, resume it, so I start running it. I put 1 on the stack, I suspend, and this time, when I suspend, I'm carrying that 1 over to my main function. Kind of like when I have an exception, I can sometimes have arguments to that exception. This tag, or this effect, has a tag type that indicates that I am carrying values over. And so now, when I do on t block 2, I'm exiting this block. What I've got on my stack is not only the continuation I just suspended, but also the payload. That's the value 1. So if I try to call the function f on it, and then resume, now when I come back, I've got f of 1 and 2. So now this is a very convoluted way of computing f of 1 plus 2 instead of 1 plus 2. If you're wondering what a realistic program might look like, we could imagine something like this, where the auxiliary function is a loop, where it just does some operation a number of times, and after it's done every operation, it suspends. Now in my main function, if I create this continuation corresponding to the auxiliary function and place it in a local variable k, now I can do a loop where I would resume what is in k, so originally it's this loop function, and then every time I do this sum operation, I would exit block 1 and I will do something else. If I replace the continuation I had on the stack into this value k, I can then repeat this loop. And what I'm doing here is simply interleaving do some operation and do something else. Now the trick when you're trying to reason about code like this is how do you give this auxiliary function a modular specification? We could imagine that these two are in different modules and we'd like to be able to reason about them separately. But in order to understand what happens with aux, when you see this suspension, you really need to know what is happening in the function that is going to call you, or at least that's the case in traditional separation logic. The way you solve this, as has been well understood for a couple of years now, is by using a protocol-based logic. We've been using Hazel, a version of Iris that is better adapted to reasoning about effects. Instead of having a weakest precondition like what we have in Iris-Wasm, we have now an extended weakest precondition. Looks a lot the same, but we've got an extra little thingy here in these angled square brackets. The way you read this is my expression E, my program E, runs safely, does not get stuck. If it terminates on a value V, then my postcondition Q holds a V. So far, that's exactly the same definition as a weakest precondition. But now, if an effect is triggered, that effect has to follow a protocol psi. Now, what does this protocol look like? It can actually be very, very general, but most of the time we're going to use a protocol that looks something like this. This is inspired by session types. It's kind of like an answer, a question-answer kind of dynamic here. The way you read this is when an effect is triggered, you want there to exist an X such that the payload of the effect is V, and you have some property P. And then if you ever resume this effect, for all y, if execution is resumed with value w, then you're guaranteed to have q. Now, to understand this better, let's just have a look at our examples again. In my first example, I'm just computing 1 plus 2. Then I can have a very dumb protocol that just says, I'm giving you nothing, I'm getting nothing back. And then I have 1 plus 2. And I should be able to prove this. Calling the auxiliary function just gives me 1 plus 2. In my second example, now I am actually having a payload carried around. So my protocol would look something like there exists an X such that what I'm giving you as a payload is X. And then what I'm getting back is f of X. And now I should be able to prove that when I call my auxiliary function, what I get back is f of 1 plus 2. In my realistic program, now it obviously depends on exactly what do some operation and do something else is, but I could imagine I have a protocol something that looks something like there exists an n such that I've done my n first operations, and then I get back some q. It's really going to depend on exactly what you're doing here, and then you should be able to reason about this auxiliary function. If we want to have a look at the slightly more technical part of things, the rules, the reasoning rules that we define for suspend and resume, the suspend rule is actually really simple. If I want to suspend with a payload V, I just need to make sure that the payload follows the protocol, which in the most general case is written like this. If I'm in the case where I'm using that session type protocol, it looks like, again, unfolding the definition. There exists an X such that my payload is equal to what is specified by my protocol. I've got the property P specified by my protocol. And if I am given that Q that I should be guaranteed upon returning, then I'm able to establish my postcondition. The rule for resume is slightly more intricate. What's happening here is I'm trying to resume a continuation K with payload V. I have to have a continuation resource corresponding to this continuation. I need to know that what is inside my continuation can be run safely. That's this weakest precondition. If this ever terminates, that's the normal termination case of my continuation running, I need to show that the postcondition here from this premise will imply what I want here. In real life, this is actually a little bit more complicated. It's not just an implication. Otherwise, you could just remove phi 0 and just use phi everywhere. But this is my normal termination clause. And then I've got an effect clause. What happens if I trigger an effect? The definition for this triple is right underneath here. What I want to show is that I am able to actually branch out of the block that is specified by the clause in my resume, and for that I know that I will be given a continuation resource, and I will be given that this continuation follows my protocol. If I unfold this definition in the case where I'm actually using a session type protocol, what happens here is I know that I will be given a continuation, I will be given an X, I will be given an address K, I will be given that property P specified by my protocol, and I will know that as long as I'm able to provide Q, I am able to run my continuation. If you see this for the very first time, this is very convoluted. It feels like black magic, and it felt like black magic to me for a long time, but it works. It's very beautiful, and in the end, it allows us to prove very interesting properties about what happens in Iris-WasmFX. So the contributions that we have provided is a full mechanization of the language together with a proof of type soundness, which was the first for this version of WebAssembly, as well as this full program logic that should help verify libraries or verify your own code when you reason about WebAssembly, when you reason about programs in WebAssembly with effects. If I want to give a more general conclusion, this work shows again that machine check proofs are possible even for industrial sized languages, like we probably already know, but this is yet another example of this being done. We think Iris is an ideal tool to reason about these industrial sized languages, and Iris-Wasm is ideal in particular when it comes to reasoning about WebAssembly and new versions of WebAssembly. Thank you very much.
Any questions? Could you please go to the...
Hi, thanks for the very nice talk. I have a question about the type safety proof. So for most versions of Iris, it has a syntactic type safety proof. For your extension with effect handlers, is it still syntactic? Should I be? Okay, sorry. Is the type safety proof for WebAssembly with effect handlers still syntactic, or did you do a semantic proof using your program logic?
We have a proof for syntactic type safety that does not rely on Iris at all. So these are two almost orthogonal contributions. But once you have the program logic, then you can prove a lot stronger things as well.
Okay, thank you.
We have a proof that does not rely at all on Iris. Iris also has adequacy to a theorem, so everything that is proved in Iris can be extracted to a formulation that does not involve Iris at all. So everything that is shown in our paper does not rely on needing to trust Iris. You need to trust our mechanization, you need to trust the Rocq proof assistant, but not Iris.
Okay, let's just thank the speaker again.